the last topic in the context of buffers is what happens when we add a strong species to a buffer. The pH definitely changes, but it only changes slightly, right? So we know we can dump a strong species into a buffer and it resists changes in pH, but what if those slight changes are things that we actually need to calculate? Or what if we just want to adjust the pH of our buffer? Well, we're going to use a strong species and we're going to use a modified version of the Henderson-Hasselbalch equation. But before we get there, we have to organize our thoughts. Remember the main sort of thought process behind a buffer is that we have HA and A minus on opposite sides of a two-way street, on opposite sides of equilibrium, all right, available to shift around as much as need be when the H3O plus concentration is affected, right? So we always have to kind of keep this in the back of our head. This is the equilibrium that's being sort of manifested, that's being manipulated as we do our changes to our buffer. So before we get to what we do with the Henderson-Hasselbalch equation, let's organize our thoughts. And we're actually going to use if tables to think about what happens. Now let's take the advantage of two different scenarios. Let's talk about two different scenarios. What happens when you add a strong acid to a buffer? pH is going to change a bit. It's going to go down a bit. But how? How do you quantify it? Well, if I add a strong acid to a buffer, what we have to realize is that the amount of acid that you have in there is going to go up. The amount of base is simultaneously going to go down. And we can see that by analyzing this reaction and thinking about Le Chatelier's principle, right? If I add H3O plus, it's like adding product. What happens if I add product, right? Equilibrium shifts from this side to this side. So what happens is a strong reaction takes place. And the A minus in solution, it finds that H3O plus that you're adding. And with a one-way street, because a strong species involved, with a one-directional reaction, what we get is we generate HA and H2O. Okay? The A minus is going to grab the H plus that you add and it's going to force it that way. So it really looks like the flip of this reaction, the reverse of this reaction. Okay? But again, it's different because it's only in one direction. So keep thinking about this. This is our buffer. It's still here. It's not flipped. It's just what's happening. But how's the buffer affected by that strong reaction? Well, if I had an initial amount of A minus that I'm just going to call Y, and I had an initial amount of HA that I'm going to call Z. Remember, if tables are for organization of moles. So if I have Y number of A minus in there, moles of A minus, and Z moles of HA. And to that reaction, I add in X numbers of H3O plus, X number of moles of H3O plus. These are completely used. These go away, and the reaction goes in that direction. And so we lose moles of A minus as the strong acid goes in there, and we make moles of HA. Okay? So if you think about it, inside our Henderson-Hasselbalch equation to start, we would have these moles in that log term and these moles in that log term. But after the addition of strong acid, we have to account for this strong movement that occurred. And so we're going to see that we're going to modify our Henderson-Hasselbalch equation by replacing whatever moles we had there to start with whatever moles we had there to start minus X, because we moved it in that direction. It's actually this direction based off of how we wrote this. We generated X more moles of HA by taking away X moles of A minus. Okay? And the same thought process occurs, but in the opposite direction for your buffer system. And this pH change might be slight, but it's definitely going to occur because we have changed that log term a bit. And like I said, once we get to the mathematics, you'll see it. Same idea, same thought process. Let's add a strong base. Okay. So let's have a buffer established with a certain amount of A minus and a certain amount of HA. What happens when we add a strong base? Well, if I throw more base in there, unsurprisingly, the amount of acid you had in there to start with goes down. And if I throw a base in there, all right, the amount of A minus you have in there goes up. Now, why does this occur? Well, from a Le Chatelier's principle standpoint, if I have a strong base in there, it takes this away. And if this gets smaller, what Le Chatelier's principle tells us, right, the strong base is going to take away H3O+. So how does the equilibrium shift? The equilibrium shifts now to the product side. So what happens is you lose HA through that shift, and you make more A minus through that shift. Another way of representing that in the context of an if table is if I have HA and I add OH minus, a strong reaction occurs, and what I get is H2O, which we don't care about, okay, and A minus. If I have an initial amount of HA in there that I'm going to call Z again, and I have initial amount of A minus, initial moles of A minus that I'm going to call Y. If I put in X moles of OH minus, they're going to go away. I'm going to lose that same number of moles, that same X from HA. And I'm going to gain that same number of moles into A minus because it's a strong reaction. It goes completely. You account for that change in this way. It will slightly affect the pH, but it's definitely a change that occurs. So if you look at this relative to our last if table, it looks like we had the same starting points for your buffer, but because we're adding the opposite species, HA actually went down and A minus went up. So this organizes your thoughts about how a strong species affects the pH of a buffer. And then what we do with this organization is we apply a modified Henderson-Hasselbalch equation. All right? You are going to use this when you have a buffer established and you add something strong to it. It looks like pH is pKa, and just because Chem 101 in your book uses moles, especially for this part, I'm going to use the version of Henderson-Hasselbalch equation that has moles in it and not concentration, but the same idea applies, all right? I'm going to put moles of A minus on the top. I'm going to put moles of HA on the bottom. That's just the normal Henderson-Hasselbalch equation. If I add, though, acid, I know that this is going to go up by an amount X. That's what we saw in our if table organization. As this goes up by X, if I add acid, this is going to go down by the same amount, by the same X. If I add base, the opposite happens. My HA goes down, all right, by an X amount based off the moles of OH minus that I've put in there, and my A minus goes up by that same amount, right? So we'll see this modified version that has not just moles of A minus and moles of HA, but moles of A minus minus plus X. And moles of HA plus minus X. And what are you going to do? You're going to use the top, and they're blue here, right, in this little example. You're going to use the top, right, choice here, the minus plus, when you add a strong acid. And that's directly from our if table statements. You're going to use the bottom choice, the plus minus, right, when you add a strong base. So it looks like a complicated expression, but the way that you view this minus plus or this plus minus is just a choice. You ask yourself, am I adding a base? Well, if I'm adding a base, I'm going to lose acid and gain base. Okay, I'm adding a base, so I'm going to use A minus plus X and HA minus X. If I'm adding an acid, oh yeah, I'm going to gain acid and lose base. All right, I'm going to use HA plus X and A minus minus X on the top. Okay, so it's a modified version of the Henderson-Hasselbalch equation. So let's revisit an example that we've already done, and let's make a change to it, and let's see what you can sort of do from like an actual practical quantitative standpoint in terms of calculations involving this X that we've now introduced. Okay, so we had a buffer for an acidic species that was just called HA, and there was some A minus in there. So we're going to revisit that last example. And what we found out in this last example is we did an unrounded pKa. We calculated an unrounded pKa that was 9.37 for 11998. Okay? There are 3 significant figures there. This HAA minus example that we went over, it had a pH that was equal to 9.17, and it had a moles of A minus that was equal to 50, and it had a moles of HA that was equal to 80. What we're going to do now is we're going to say, okay, we did this problem, we established this buffer. What would I have to do? How many moles of acid? And let's make sure we understand. How many moles of strong acid must be added to get a pH that's equal to 9? So you might say to yourself, okay, what's my starting point? I have a buffer and it's established. To that buffer, I'm adding a strong species, and I have a new target pH. We're going to change these moles as we add the acid. This pH is going to go away, and we're eventually going to reach this target. Well, how do we get a lower pH? What happens if we add a strong acid? My acid moles are going to go up. Simultaneously, as these moles go up, right, the base moles go down. Okay? X will be the number of moles of strong acid that I'm adding. So what I'm going to do is I'm going to set up a modified Henderson-Hasselbalch equation. X will be the moles of acid I have to add. If I can figure out how to solve for that X, and I have you do a lot of the algebra yourself, but if you can figure out how to solve for that X, then you're good to go. You know directly what this answer is. So here's how the setup looks. pH equals pKa plus the log of moles of A minus over moles of HA. I'm going to use the modified version because I'm adding a strong species. I'm adding an acid, so this is going to go up. Right? I'm adding an acid, so the base is going to go down. I'm not going to use my old pH. If I use my old pH, my X will be 0. Right? Because then I'll have my old moles in there. I'm going to use here my new pH, all right? I'm going to put my 9.00 here. That's my target. I'm making a change to an established buffer to get a new pH, okay? I'm going to use my same pKa. I'm going to use my unrounded version, 9.37 for 11998. My old moles of A minus, right, were 50. That's going to change by an amount X. My old moles of HA were 80. That's going to go up by an amount X. So everybody see the setup. We have a new pH because we're changing the amount of acid and base because a strong species was put in there. This will give me the moles of strong acid I have to get. As always, please check my work, okay? I'm going to leave you to do this algebra because it's great practice. Just if you can't really see it real quick, you're going to bring this over here. You're going to get rid of the log. You'll then have two x's that you have to solve for. You gather your x's on one side of the equation. You gather things that don't have an x on the other side of the equation. You do the algebra. And what you end up with this algebra is you end up with an x that's 11.385. When I do it, I think I get two significant figures. Again, please check my work. Solve for this x. So the final answer is the moles of strong acid to the correct number of significant figures. It looks like we have to put in 11 moles, right? We have to put in 11 moles. So if you go back up here, we dump in 11 moles of strong acid. This becomes 91.385. This is 50 minus 11.385, right? These values change, and that's why we get a new pH for this buffer. So it's one of the most algebraically intense problems having to do with buffers, but again, it's not beyond your skills. It's again using the Henderson-Hasselbalch equation form, but if you're adding, right, a strong acid, you put a plus x here and a minus x here. Say we wanted to get to pH 10, right, from our original buffer. What we would do is we would put 10 here, and then we would have to add a base. Remember, this used to be 9.37 with the 50 and the 80. So how do I make this 10? How do I make it go up? This would have to become a positive, and that would have to become a negative. You would have to add base to raise the pH if my new target was 10. And that's the critical step, and that's why I showed you the if tables. That's where you have to really just make sure that you understand what this setup is about. As always, send me questions. You will see these sorts of problems in your book and in Chem 101. Don't be afraid of them. You can do it. Just make sure you understand the chemistry first, where the plus x and the minus x go, and you'll be set in terms of what your answer is.